precious family photos. All right. Yeah, this whiteboard is getting worked out totally. Okay, we've got it. We've got to count. Yeah, throw your bets in there. Whoever wins gets a free voucher to Taco Bell for one bean burrito from me. All right. So there we go. Uh-oh. All right. Oh, going for the office hours tonight. I like that, Jose. I like that. All right. So we are talking about angular momentum. In the words of Allen Iverson, are we talking about practice? I guess we are. So man, I'm losing it. It's been a long semester. Okay. So in this case, that's what we talked about last time. Angular momentum. This was the fundamental way of calculating it that you could use in any situation ever. However, we saw that there are some tricks that are usually used. Specifically, sometimes we use MVR perpendicular, or for extended objects, we use I omega and the right-hand rule. We mentioned that they match up. If you notice that the moment of inertia is mr squared for point mass, we see that MVR and mr squared omega are the same thing. We talked about if external torque is negligible, if there's no net external torque, angular momentum is conserved. And in particular, we talked about if you have two objects that rotate with a collision versus a rotating object that changes shape. Now, I wanted to skip ahead to a certain page here, and then we're just going to do some practice problems. Where is it? This is it. I think we haven't discussed this yet. I'm on page 93 in the workbook, people. 93. All right. So in this case, I just want to emphasize we have basically learned a few tools today, and I was alluding to this when we were discussing the final exam. We have conservation of momentum, conservation of angular momentum, conservation of energy, and I guess you could argue we have a couple of other things. We have sum of forces. We know how to do sum of torques. Let me just write this all in so you've got it in one spot. And again, we also have kinematics. And that's both rotational 1D, 2D. So that's 1D, 3D, and rotational. That's our subset. Those are all of the tools we have learned so far, basically, right? Momentum, angular momentum, energy, chapters 8, 9, and this was chapter 8. This was chapter 9. This is chapter 11. And then the rest of this stuff was the other chapters. So think about it. That is a pretty full quiver of tricks to use to analyze problems. And to be honest, those are all of the big fundamental things we need to understand to analyze everything else in mechanical systems, right? Like blocks, springs, cars, whatever. Now, there's going to be some other things you learn later in physics, such as electricity. We're going to build on that by saying, okay, what terms do I need to add to the energy equation when I deal with electricity or magnets? How are those added to forces and torques for electricity and magnets? But we're going to use the same tools over and over and over again. So if all of this torture that I've been putting you through of struggling and working and doing this so much, just remember, these are the building blocks of every engineering discipline and every physics course you take afterwards. So if you had to choose one class to really, really, really get the basics down, this is it. This is that class where doing more work than you think is necessary ends up paying off. For example, I don't think I told you this, but I had a student come in. He was a student in my 161 class. He didn't pass. He had to drop. He had to retake. And then he took my 163 class. And he eventually used me as a letter of recommendation for an internship at, I think it was UCSD, San Diego, an elite school. He got the internship, and he's an engineer. And he was saying that during the interview, everything that we were doing in physics lab, the presentations, the coding, etc., came up in his job interview for this internship, and he got it basically because he could say things from this class that he was doing. Now, this might be a special case, but I am trying to do you right. I know it's a lot of work. I know it's painful, but people are getting jobs. I talked to another guy that had me for class, and all the coding stuff and all the extra little things I made him do got him an internship. And once you get an internship at one of these prestigious schools and get a rec letter from it, you're set. So I think this is trying to motivate you. Anyways, that's the big deal up to this for this entire course. Basically, we know how to do this, and if you do all the work, your odds of getting an internship and a job should be good. So any questions about these big three conservation laws while they're sitting up here on the screen? The trick is you need to know when they apply. So if this is true, then you can use it. If this is true, then you can use that. And finally, if this is true, then you can use that. That's something that I want to be, beaten into you. The rest of the questions in this chapter from page 93 on focus on not necessarily doing the work, but knowing which equations apply. And this is going to show up on your final. So I'm going to literally ask something and say, which conservation laws show up? So if you do these problems, you'll get a feeling for when should I do this? Why should I do this? So if you want to do these ones here, read through them, look at the answers. And I forget what I said on the homework requirements. I think I said you don't have, I don't remember if I told you to do these or not. But basically, I think I wanted you to look at these and read the answers, but not spend all the time doing the whole work for every single one of these. So just know that's the point of this stuff. All right. So it's just high speed repetition to lock in the content. For example, this one, look at this one, 11.20. During the collision, which conservation laws apply? Assume the system includes the rod and the clay. It's in deep space. What do you think?
Conservation of angular momentum.
That's true. What about the others? Do they apply or not?
I don't think, or it's perfectly inelastic, so the energy does not count.
Energy does.
It does?
Meaning energy initial equals E final. So conservation of energy applies here. That word, so elastic means bouncy, rubber bands, conserves energy like a spring.
Oh, I didn't even see that.
Yeah. Sorry, I rushed you.
I assumed because I didn't read the question, but I assumed that it got stuck to the rod. And so I was like, if it got stuck to the rod, then it's not elastic.
You're right. So like this one up here, E initial is not equal to E final. Do you agree? Yeah. And so this is what I was saying is just kind of read through it, and it will practice your ability to read these questions, correctly snag the right tools. What about momentum? So I think Esteban said L initial equals L final, right? Angular momentum is conserved. There's no external torque because there's no external forces. So what about linear momentum? What do you think?
I would say it also applies because there's no pivot. I mean, the pivot is over the center of mass, right?
Yep. So the pivot is essentially the center of mass in free space. Now, actually, in this case, how many unknowns do you think I could give you for this particular problem? So let's think about how many equations do you have here?
Technically 3.
Actually, this is 3 all by itself, but do you agree that the Y and the Z probably don't matter?
Yeah, because we consider coordinate system to just follow the one.
Yeah, basically
coordinate.
we only have motion in the x direction, but technically we have 3 here. And then this one, you could say technically we have 3. So we actually have 7 equations here. In practice, this is effectively only 3, like Esteban said, right? There's rotation about one axis, translation about one axis, and energy is a scalar equation. So if there's 3 equations, how many things could be unknown if you were going to solve this problem?
You can have 2 unknowns.
3 equations, 3
unknowns.
unknowns. Yeah. So, for example, the final speed of the rod, the final speed of the ball, and probably the final rotation speed of the rod would be the things that would be, yeah. Got it? So, anyways, if you want to lock this stuff in, you could see all these little things. For example, what moment of inertia should you use? Okay, got it. So this will kind of cue you in as to some of these, and there's some variations on here. Yeah, and so some of them have pivots, some of them don't. Some of these have like this kind of situation, blocks on a plane. There's different scenarios here, and this is one we're going to work on today, probably a zombie on a disc. The old zombie on a disc problem. Anyways, just thought I'd let you know that. There's some notes in there. Look at this one from chapter 8. You could decide if what applies here. And so I'm going to let you guys do that. But let's get to some practice now. Okay. Oops. All right. Let's look at 11.16. So take a look at that one. I'm going to erase the whiteboard and see if it falls over. Still holding. Maybe. Whoa, this is really bad. And something I thought I might do, I actually want to take the time, since we have it, I'm going to actually open up some breakout rooms for this. I don't usually do this. I'm going to randomly assign, but I'm going to make them extra big. Okay. That way there's not people ghosting you in those rooms or something. So I'm going to open these up. I just made 3 breakout rooms and I want you guys to be able to talk about them. And so hopefully there's at least a couple people in each group. I see that some of you, I recognize your partners are there. So everybody should have, I think, at least one partner from their usual group. So you guys, hopefully this will work. And this is not for a grade. I just want you to take a few minutes to talk about it without me hovering over you. Go ahead and jump into there. And this is on page 92, problem 11.16. Go for it.
Do we have to solve it, or
just try to solve it and talk to people about it while you're doing it and see if you could get a start on it without looking at the solution? Okay. Just try to talk it through with your partners.
all right, thank you.
Yep. Sorry about that, Sophia. I'm going to try looking at question 11.16 in breakout rooms. It's not for a grade. I just want to give you an opportunity to talk with some people without me.